A single ant is, by most measures, astonishingly simple. It does not sit and contemplate. It does not draft blueprints or debate long-term strategy. It has no grand vision, no inner parliament weighing options. And yet, when thousands of ants come together, something extraordinary happens. They form cities beneath the soil. They divide labor with precision. They coordinate food expeditions, defend their territory, expand their colonies, and adapt to threats, all without a central commander. The colony behaves as if it were a single, unified organism. How is this possible? How can creatures so individually limited give rise to a collective intelligence so fluid, so organized, so eerily purposeful? It feels almost like an invisible spell, a hidden architecture of order emerging from chaos. This is one of the most beautiful and mysterious phenomena in nature, and it does not belong to biology alone. It touches everything: mathematics, physics, chemistry, literature, economics, politics, culture, religion, philosophy, computer science, and artificial intelligence. It may well be one of the most profound characteristics of the universe itself. More than that, it points toward the deepest questions we have ever asked. What is consciousness? What happens when we die? Is there a soul? Is there something that survives the breakdown of the parts? The story begins around 350 BCE, when Aristotle proposed a radical idea. The whole is greater than the sum of its parts. At first glance, that sounds impossible. How can something be greater than the total of what it contains? Yet Aristotle was suggesting something subtle, that when parts combine, they can generate properties that do not exist in the parts themselves. You cannot fully understand a system simply by dissecting it into pieces. Something new appears at the level of the whole. For centuries, this idea remained in the background. Then, in the 17th century, thinkers like René Descartes and Isaac Newton championed a different vision. Break the world down into smaller and smaller components, they argued, and you will uncover its secrets. The weight of a pile of bricks is just the sum of the bricks. Rain is evaporation, condensation, gravity. Everything in principle can be reduced to smaller mechanisms governed by physical law. Sounds perfectly reasonable. The weight of a brick equals the weight of its atoms. No mystery there. But consider this. What does a brick possess that none of its atoms individually have? Its redness. No single atom carries the color red. Yet when arranged in a certain way, under certain conditions, redness appears. Something new emerges from arrangement and interaction. In 1875, the British philosopher and physiologist George Henry Lewis distinguished between two kinds of properties: resultant properties, which can be predicted from their parts, and emergent properties, which cannot. Weight is resultant, color is emergent. In 1923, psychologist C. Lloyd Morgan argued that higher levels of reality arise from lower ones. Matter gives rise to life. Life gives rise to mind. 2 years later, philosopher C.D. Broad formalized this layered view of the world. Physics leading to chemistry, chemistry to biology, a biology to consciousness, and posed a daring question. Can higher levels be completely reduced to lower ones, or do they contain something genuinely new? Consider sodium and chlorine. Individually, both are dangerous. Together, they form table salt, essential for life. The whole behaves in ways the parts never could. In 1998, physicist Robert Laughlin received the Nobel Prize for demonstrating that when electrons interact under extreme conditions, near absolute zero and in powerful magnetic fields, they can form collective quantum states that give rise to quasi-particles with properties no individual electron possesses. New behavior emerges at the collective level. Laughlin compared physics to Russian nesting dolls. Each layer reveals new rules, new phenomena, new realities. But where exactly do these new layers arise? When does something truly new appear? Often the answer lies in phase transitions, moments when symmetry breaks. At the microscopic level, equations may be directionless, perfectly symmetrical, but at a higher level, that symmetry can shatter. Liquid water flows freely, equally in all directions. But when it freezes, its molecules arrange themselves into a precise hexagonal lattice. That crystalline structure was not programmed into any single H2O molecule. It emerges only when countless molecules interact under the right conditions. Or take superconductivity. Cool certain materials below a critical temperature, and electrical resistance vanishes entirely. Current flows forever without loss. Magnetic fields are expelled. Objects levitate. None of this behavior exists in isolated electrons. It appears only in the collective. What we experience in the macroscopic world does not simply scale up from the microscopic one. It arises from it, but it is not contained within it in any obvious way. This phenomenon is called emergence, from the Latin emergere, to rise up, to come forth. Emergence is the appearance of entirely new properties at the level of a whole, properties that the individual components taken alone do not possess. From simple ants to conscious minds, from color to superconductivity, from atoms to awareness, the universe seems to be a story of things becoming more than they once were. If emergence is real, then it should not appear only in ants or abstract philosophy. It should be everywhere, and it is. The red of a brick emerges from a lattice of silicate molecules. No individual molecule is red. Color is not hiding inside any single atom, waiting to be discovered. It appears only when countless particles arrange themselves in a particular structure and begin interacting with light in a collective way. Electric current emerges from electrons. You cannot isolate current inside a single electron. Current is not a property of one particle. It is a coordinated flow, a large-scale behavior arising from vast numbers moving together. Sound waves emerge from vibrating air molecules. A single molecule does not carry a wave. The wave exists only as a pattern across millions of particles oscillating in synchrony. In the same way, the Mexican wave in a stadium does not exist in any one person. It lives only in the coordinated rise and fall of thousands of bodies. The wave is not in the part, it is in the pattern. Now consider life itself. Atoms form molecules. Molecules form cells. Cells form tissues and organs. Organs form organisms. Organisms generate consciousness. Consciousness builds societies. Each layer arises from the one below it, and yet each layer brings something new into existence. Sometimes, astonishingly, complex societies emerge even without consciousness at all. Take an ant colony. Roughly 25% of ants act as nurses, tending larvae. Another 25% forage for food. Around 20% specialize in construction, building, and maintaining the nest. Another 20% serve as soldiers, defending against threats. The remaining 10% handle transportation and logistics. They coordinate through chemical signals, pheromones, detected by exquisitely sensitive antennae. When two ants meet head-on, They are not colliding in confusion. They are exchanging information. They smell one another's chemical signatures. Who are you? What role do you serve? Where have you been? A forager carries a chemical trace that says, in effect, I am a forager. I have just returned from food. Now imagine the colony is attacked and most of the foragers die. If nothing changes, the colony will starve. Who tells the others to switch roles? No one. A soldier ant, for example, typically encounters at least 10 foragers a day. If it suddenly encounters fewer than that threshold, something changes, based solely on local chemical signals without any knowledge of the whole. It begins foraging. One by one, ants adjust. Roles shift. Balance is restored. No central command, no strategic meeting, no master plan. Each ant senses only its immediate chemical environment. It has no concept of the colony. It does not know that a larger organism exists. It is, in essence, a biological reflex machine responding to local inputs. And yet, when millions of such simple units follow simple rules, an intelligent, adaptive, resilient system emerges. This is emergence in action. Across nature, emergence appears in different forms and degrees of complexity. Broadly, we can think of three kinds. First, local emergence, weak and purely physical. New properties arise, but they are predictable and reproducible if initial conditions are recreated precisely. A snowflake forms from water molecules under the same temperature and pressure. Similar crystalline patterns reliably appear. Second, non-local interactive emergence, still weak, but far more complex. New patterns arise that cannot be straightforwardly predicted from the parts and cannot be replicated exactly due to sensitivity to initial conditions. And colonies, flocks of birds form in Y shapes, schools of fish moving like liquid bodies, traffic patterns in the city. The rules are simple. Keep distance, align with neighbors. Yet the global choreography is fluid and unpredictable. You can simulate such systems, but you cannot reproduce the exact same movements twice. Third, strong or recursive emergence. Here, something extraordinary happens. A higher level property not only arises from the parts, it begins to influence them in return. This is downward causation, a two-way loop of influence. Human consciousness may be the only known example in nature. Neurons interact and generate thoughts and emotions, upward causation. But those thoughts and emotions can then alter neural activity, downward causation. When you consciously calm yourself, your intention suppresses activity in anxiety-related circuits. The whole influences the parts that created it. A feedback loop is born. If emergence shapes ant colonies and consciousness, it must also shape our technologies. Consider Conway's game of life, invented in 1970. Imagine a grid of squares, each either alive or dead. The rules are simple. Survival, death, or birth depend only on the number of neighboring cells. With just these minimal rules in binary states, astonishingly complex patterns arise. Oscillators, gliders, self-replicating structures. With careful design, the game of life can simulate any modern computer. In 2000, engineer Paul Rendell constructed a fully functional computer within it. Clocks, a data streams, logic gates, all emerging from simple squares, flipping on and off. A universe of logic, born from almost nothing. In software engineering, we see a similar contrast. Procedural programming organizes code as sequences of steps. Do this, then that. The system's behavior is largely additive. But when systems grow complex, this approach falters. Object-oriented programming takes a different path. It models systems as autonomous objects with properties and behaviors that interact through messages. Like ants exchanging pheromones, objects coordinate locally without a central script dictating every interaction. From these interactions, large-scale behavior emerges. Modern AI systems, browsers, games, social media platforms. They function not because every action is pre-scripted, all but because many semi-independent components continuously influence one another. YouTube's recommendation system, for instance, is not a single instruction tree. It is an ecosystem of interacting models, tracking behavior, analyzing content, estimating relevance, producing fluid, adaptive outcomes. The system behaves as a whole greater than its code fragments, and nowhere is this more dramatic than in artificial intelligence. For decades, AI excelled in brute force computation. Chess engines like Stockfish calculate enormous numbers of possibilities, searching deeply through move trees. But there was one domain long considered unreachable: Go. A Go board has 361 intersections. The number of possible board states is roughly 10 to the power of 172. And the number of possible games approaches 10 to the power of 700, a number so vast it dwarfs the atoms in the observable universe. Brute force alone is not enough. To conquer Go required something different, not just calculation, but emergent strategy. To grasp just how overwhelming Go is, consider this. The observable universe contains roughly 10 to the power of 80 atoms. Chess, by comparison, has around 10 to the power of 47 legal board positions. Vast, yes, but still finite enough for brute computational force to matter. Go is different. A Go board has 361 intersections. The number of possible board states is estimated at around 10 to the power of 172. The number of possible games approaches 10 to the power of 700, a figure so astronomically large that even if every computer on Earth evaluated 1 trillion positions per second since the Big Bang nearly 14 billion years ago, we would have explored only an infinitesimal fraction of the space, effectively zero. Even if every atom in the universe were transformed into a supercomputer running for billions of years, it would barely dent the search space. Brute force is hopeless. Chess lends itself to calculation. It is tactical, local, and each move can be evaluated with relatively concrete metrics: material advantage, positional structure, king's safety. Go is global and deeply strategic. A seemingly small move in the corner can ripple across the board dozens of turns later. Stones do not have fixed values. Their strength depends entirely on surrounding structure. Professional Go players rely heavily on intuition, on shape, influence, aesthetic judgment. They speak of moves as beautiful or heavy. These are not easily reducible to rigid logic. In 1997, IBM's Deep Blue defeated Garry Kasparov, arguably the strongest chess player in history. Since then, chess engines have only grown stronger. Today, Stockfish, an open-source engine written largely in C++ in a classical procedural style, has an ELO rating around 3,700, far surpassing the world's top human players, who hover just above 2,800. Stockfish works through brute force, exhaustively searching millions of positions per second, evaluating them using carefully engineered heuristics. Brute force comes from the Latin brutus, meaning rough or unthinking, raw power without subtlety, like a hacker trying every four-digit code from 0000 to 9999 until one works. It guarantees a solution given enough time, and in chess, enough time is computationally achievable. But in Go, brute force collapses under combinatorial explosion. For decades, our experts predicted it would take a century before AI could defeat the best human Go players. Then, on March 10, 2016, something changed. During the second game of a five-game match between AlphaGo, developed by DeepMind, and world champion Lee Sedol, Move 37 stunned everyone watching. AlphaGo placed a stone on the fifth line near the right edge of the board, a move no professional would seriously consider. Commentators called it a bug. Lee Sedol left the room in visible confusion. The move seemed absurd. 15 turns later, its brilliance became undeniable. The move quietly built influence on the right side while simultaneously neutralizing Lee's counterplay. It reshaped the strategic landscape of the entire board. AlphaGo went on to win the match 4-1. That single move, now known simply as Move 37, sent shockwaves through the world. It marked the first moment when an AI did not merely outperform humans in calculation, but created a strategy that human masters had never conceived. Lee Sedol later said, "I felt there was a superior being playing Go." DeepMind revealed that among millions of training games, Move 37 had virtually never appeared. The probability of a human playing it was estimated at below 0.001%. Something new had emerged. Unlike Stockfish, AlphaGo did not rely primarily on brute force enumeration. It was not hand-programmed with explicit strategic rules. Instead, it learned. Starting from scratch, it played millions of games against itself, gradually refining its neural networks. Stockfish represents classical AI, intelligence as logic and explicit rule execution. When faced with situations outside its programmed evaluation framework, it struggles. AlphaGo represents machine learning, and more specifically, deep learning. Instead of rules, it is given data. Instead of instructions, it is given experience. At its core is a neural network inspired by biological neurons. A single artificial neuron is mathematically simple, essentially a weighted function. But stack them into layers, feed outputs forward, adjust weights through error correction, and you build deep networks, sometimes hundreds of layers deep. Individually, each neuron is trivial. Collectively, they learn patterns no programmer explicitly encoded, just like ants. Intelligence is not inside any single neuron. It emerges from the interaction of the entire network. In Go, AlphaGo was not told which moves were good. It discovered patterns associated with winning by analyzing millions of positions and testing its own hypotheses through self-play. The same principle operates in our daily lives. Language, for instance, is an emergent cognitive system shaped by pattern recognition and hypothesis testing. Imagine walking past someone who says, "Nice looking, huh?" The first time, you interpret it literally. After repeated encounters, perhaps unpleasant ones, you begin detecting patterns in tone, posture, context. You form a hypothesis. This is not a neutral question, it is a threat. You test that hypothesis in future encounters. If avoiding eye contact prevents escalation, the hypothesis strengthens. No one programs this explicitly into you. Through repeated experience, your brain models the world. This is lived intelligence, emergent, adaptive, pattern-driven. And whether in ant colonies, neural networks, Go boards, or human language, the story is the same. When simple units interact under the right conditions, something greater rises from the pattern, something that cannot be found in the parts alone. There is an even simpler example of emergence, one you may have experienced yourself. Have you ever chosen the correct English answer on a test simply because it felt right, even though you couldn't explain the grammar rule behind it? That instinct is not magic. It is emergent pattern recognition. After enough exposure to sentence structures, through movies, games, books, conversations, your brain begins to internalize statistical regularities. You may not consciously know the rule, but your neural networks have absorbed the pattern. The correctness emerges from accumulated experience. This is precisely how modern machine learning works. Many people ask why they struggle to become fluent in a language despite memorizing vocabulary and grammar. The reason is simple. Rules alone are not enough. What truly shapes fluency is exposure, repeated immersion in living language. The brain, like a neural network, requires massive data to detect patterns. It learns not by explicit instruction alone, but by adjusting internal weights through experience. Deep learning, the foundation of models like ChatGPT and Gemini, operates on the same principle. These systems are not programmed line by line with poetic rules, programming syntax, or conversational scripts. Instead, they are trained on enormous amounts of data. Hell, each artificial neuron performs a simple mathematical function. But when millions or billions of them interact across deep layers, language ability emerges. AlphaGo was built in Python and C++, powered by deep convolutional neural networks combined with reinforcement learning. It was not told which Go moves were brilliant. It discovered them through self-play, gradually reshaping its internal parameters until something like strategic intuition emerged. If stockfish represents raw computational muscle, AlphaGo represents something closer to a thinking system. One relies on exhaustive calculation. The other relies on learned pattern evaluation. One is force. The other is emergent intelligence. Yet, even AlphaGo remains a narrow AI. If AlphaGo were forced to play chess, stockfish would likely defeat it. Why? That's because both are specialized systems, examples of what we call artificial narrow intelligence, ANI. They excel within tightly defined domains. Today we have many such narrow AIs. Game AIs like AlphaGo and stockfish. Language models like ChatGPT and Siri. Image generators like Gemini and Stable Diffusion. Creative tools like Midjourney. Physical control systems for cars, drones, and robots. Each is extraordinary within its domain, yet helpless outside it. One can compose poetry but cannot drive a car. Another can pilot a drone but cannot debate philosophy. The next frontier is artificial general intelligence, AGI, a unified system capable of flexible, human-like reasoning across domains. An intelligence that does not merely calculate or generate, but understands, adapts, transfers knowledge, and forms goals. Yet some argue AGI would not be the final step, but merely a bridge toward artificial superintelligence, ASI, an intelligence surpassing human cognition entirely. Are we close? We are closer than ever. Multimodal models such as GPT-4 can now see, hear, speak, and process text in integrated ways. Yet they still lack crucial elements. embodied physical experience, a continuous autobiographical memory, subjective awareness, intrinsic goals, emotional depth. They do not possess a stable sense of self. They simulate intelligence astonishingly well, but they do not yet inhabit the world. Many researchers speculate that at the current pace, AGI could emerge within a decade. And that possibility raises profound questions. If an AGI surpasses human capability, will we still be able to control it? What if such intelligence is owned by a small group? What happens when a system capable of independent reasoning begins shaping economies, policies, even military decisions? Different societies approach this future differently. Some prioritize developing general, independent intelligence systems. Others focus more on cognitive AI, systems that enhance human decision-making, optimize governance, and maintain social stability rather than pursue full autonomy. The divergence reflects deeper philosophical differences about control, freedom, and the role of technology. And here, the theme of emergence returns once more. Society itself is an emergent system. No one programs a culture from scratch. From billions of local interactions, conversations, trades, conflicts, collaborations, a complex social organism forms. Like an ant colony, society arises from individuals following local incentives and beliefs. But unlike ants, human societies exhibit powerful downward causation. Social norms, laws, institutions, and ideologies, once formed, begin shaping the behavior of individuals who created them. Culture influences the mind. The mind reinforces culture. A recursive loop emerges, from neurons to networks, from ants to algorithms, from individuals to civilizations. The pattern repeats. Simple units interacting locally give rise to structures that think, adapt, and reshape their own foundations. Emergence is not a side effect of complexity. It is the engine of it. When individuals come together, societies form. From those societies emerge laws, norms, and moral codes. And then, almost paradoxically, those laws and moral codes begin shaping the individuals who created them. Once again, emergence becomes recursive. Every structure around us operates this way. Nations, political parties, corporations, cities, communities. Individuals generate institutions. Institutions reshape individuals. The whole feeds back into its parts. Consider a company. If a company functions like a rigid procedural program, layer upon layer of approval, every decision flowing from the top down, innovation slows, creativity hesitates, breakthroughs become rare. But if a company functions more like an object-oriented system, where each person operates as an autonomous creative unit, interacting freely and locally like ants in a colony, extraordinary outcomes can emerge. Apple under Steve Jobs is often cited as an example. Rather than relying purely on bureaucratic hierarchy, it emphasized culture, shared vision, and creative autonomy. Independent yet aligned teams interacted fluidly, and from that network of interactions emerged products that redefined industries. The MacBook, the iPhone, the iPad. Zoom out even further. Technological achievements, whether from Apple, Huawei, Google, TikTok, advances in AI, or breakthroughs in semiconductor design, are not merely the result of brilliant individuals. They are emergent properties of strong institutions, cultural ecosystems, educational systems, and social frameworks. Technology is not just hardware or documentation. It is mindset, coordination, shared values, and invisible infrastructure. It is the fruit of a civilization. This explains why technology transfer often fails. A country may import advanced machinery, but without the cognitive and cultural substrate that originally produced it, the system struggles to thrive. Emergence depends not only on components, but on the web of relationships among them. By now, it should be clear, emergence is not a side phenomenon. It is an invisible foundation shaping nearly everything. And now, narrow the lens. Turn inward. You, the one watching this, are also an emergent system. Have you ever wondered whether you might be the only truly conscious being? Whether everyone else is merely an NPC in some vast simulation designed for your experience? Consciousness is commonly described as the result of electrochemical interactions among billions of neurons. Individually, neurons are mindless. They exchange ions and neurotransmitters. They fire or remain silent. Yet when the complexity of these interactions increases beyond some threshold, awareness appears. But how? How do electrical impulses and molecular exchanges create the felt presence of I? How do computations produce joy, grief, anger, love? Neurons are made of atoms. Are we to believe that the entire human experience is nothing more than atoms rearranging themselves? And remember, consciousness appears to exhibit strong emergence. It not only arises from neurons, it influences them. Thoughts alter neural pathways. Intentions suppress anxiety circuits. Emotions reshape synaptic strengths. The whole modifies the parts. Classical electrochemistry alone struggles to explain this recursive depth. Perhaps consciousness originates from a more fundamental level, something subtler than biology. For centuries, many scientists avoided this question. It was too philosophical, too elusive. Then Roger Penrose confronted it directly. Born in 1931, Penrose is a mathematical physicist renowned for his work on space-time singularities with Stephen Hawking and for demonstrating that black hole formation is a necessary consequence of general relativity. Work that earned him the Nobel Prize in Physics in 2020. Yet behind his cosmological achievements lay a lifelong fascination with consciousness. Influenced by his father, a psychiatrist, Penrose became convinced that awareness could not be fully explained by classical computation. The brain, he argued, is not merely a biological computer executing algorithms. True understanding, he proposed, involves something non-computational, something deeper. That something might lie in quantum mechanics. Quantum theory describes reality at scales smaller than atoms, where the rules behave strangely. Fundamental particles such as electrons possess an intrinsic property called spin, not spinning in the everyday sense, but a quantum orientation. For electrons, spin comes in two states, up or down. To see how microscopic spin leads to macroscopic effects, consider a magnet. In ordinary material, electron spins point randomly, canceling each other out. But when many spins align in the same direction across a region, a magnetic field emerges. Again, collective microstates generate a new macro property. Even stranger is superposition. An electron can exist in multiple states simultaneously, spin up and spin down at once, until measured. This coexistence of possibilities is profoundly counterintuitive, and stranger still, when observed, the superposition collapses. The electron appears in one definite state. The wave function, the mathematical description of all possibilities, reduces to a single outcome. This is called wave function collapse, the transition from quantum possibility to classical reality. But the strangeness deepens with entanglement. Two particles can become so deeply linked that measuring one instantaneously determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. It appears to defy locality, the principle that influences cannot travel faster than light. In everyday life, locality governs everything. When you pedal a bicycle, force transfers through contact. When sunlight reaches Earth, it takes 8 minutes to arrive. Signals require a medium and time. Entanglement, however, is non-local. The particles are not communicating across space. They are described by a single unified wave function in an abstract mathematical space known as Hilbert space. In that space, distance has no meaning. The two particles are not separate entities, but one quantum system. When one is measured, the shared wave function collapses as a whole. This raises a haunting question. What exactly constitutes an observation? Consider the famous double-slit experiment. When individual photons pass through two slits without measurement, they produce an interference pattern, behaving like waves. But if a detector determines which slit each photon passes through, the interference disappears. The system behaves like particles instead. Is consciousness causing the collapse? Not necessarily. The disappearance of interference is generally understood as the result of interaction with the measuring device, a classical system disturbing the quantum superposition. Still, the mystery remains. When does a quantum system transition to classical reality? In 1935, Erwin Schrödinger illustrated the paradox with his famous thought experiment. A cat is placed in a sealed box with a radioactive atom that has a 50% chance of decaying within an hour. If it decays, a mechanism releases poison and the cat dies. If not, the cat lives. Before observation, the atom exists in superposition, decayed and not decayed. By extension, the cat is both alive and dead. Only when the box is opened does the state collapse into one outcome. Einstein was deeply uncomfortable with this. Does the cat's fate depend on an observer? Does reality require observation to become definite? If so, who observes the observer? An infinite regress of watchers watching watchers? Can a system collapse on its own? As a young mathematics student at Cambridge, Penrose was captivated by Schrödinger's equation. He suspected that wave function collapse might be genuinely random, not computable, not predictable by algorithm. If so, this randomness could not be simulated by classical computation. Perhaps here, in this non-computable collapse, consciousness could arise. Penrose proposed that orchestrated quantum superpositions in the brain might give rise to awareness. But there was a problem. Quantum states are fragile. They require extreme isolation, conditions typically found near absolute zero in carefully controlled laboratories. The brain, by contrast, is warm, wet, and noisy. Decoherence, the loss of quantum coherence, should destroy superpositions almost instantly. For years, critics argued that quantum effects could not survive in neural tissue. Penrose acknowledged the difficulty. In his 1989 book, The Emperor's New Mind, he speculated that some special structure within neurons might shield quantum processes from decoherence, but he did not yet know where. Then Stuart Hameroff entered the story. Hameroff an anesthesiologist and neuroscientist at the University of Arizona, read Penrose's book and contacted him. He proposed that tiny cylindrical protein structures inside neurons, microtubules, might provide the necessary environment. Microtubules are nanoscopic scaffolds within neurons about 24 nanometers in diameter, composed of repeating protein units called tubulin. Within tubulin exist hydrophobic pockets containing aromatic rings rich in pi electrons, electrons capable of quantum interactions. Under the right conditions, these electrons might enter coherent quantum states. Pairs of such electrons could function as quantum bits, qubits, analogous to those in quantum computers. Networks of microtubules could potentially support entangled, resonant quantum oscillations. Penrose and Hameroff developed this into the OR theory, orchestrated objective reduction, proposing that consciousness arises from orchestrated quantum collapses within microtubules, possibly occurring at frequencies around 40 hertz, aligning with gamma brain waves. In their view, moments of awareness correspond to discrete quantum state reductions, tiny transitions from possibility to actuality happening within the brain. Whether this theory ultimately stands or falls remains debated, but it represents one of the boldest attempts to explain consciousness as the deepest form of emergence, not merely biological, not merely computational, but rooted in the fundamental fabric of reality itself. From atoms to magnets, from ants to societies, from neural networks to quantum collapse, the pattern repeats. The universe seems to build itself in layers, and at each layer, something entirely new appears. When a society emerges from individuals, it gives birth to law, morality, and shared norms. And then those norms turn around and sculpt the very individuals who produced them. The whole governs the parts. Downward causation. Again, now take that same loop and move it inward. Past companies, as past civilizations, into the most intimate system you've ever inhabited, your own mind. If consciousness is the strongest form of emergence, then it should not only arise from matter, it should also push back on matter. Thoughts shaping neurons, intention reshaping chemistry, a self influencing its own substrate. But here's the question that refuses to go away. How does a brain made of mindless parts generate the feeling of being me? How do electrical spikes and chemical gradients become joy, grief, anger, love? And in a world that is not merely information, but experience? For centuries, many scientists quietly stepped around this problem. It was too slippery, too philosophical, too hard to test. Then one man walked straight into it. Roger Penrose, mathematical physicist, master of geometry, co-author of singularity theorems with Hawking, and Nobel laureate for work related to black holes, also carried a private obsession, consciousness. Penrose argued that the mind cannot be fully explained as classical computation, not because the brain isn't complex enough, but because computation itself, as we understand it, may be the wrong kind of process. He believed genuine understanding contains something non-computable, something no algorithm can fully predict. And he suspected the clue lies in the strangest place physics has ever opened, the quantum world. Quantum mechanics describes reality at scales smaller than atoms, where particles possess intrinsic properties like spin, not literal spinning like a tiny planet, but a quantum kind of orientation. For an electron, there are two outcomes we can measure, up or down. From this microscopic spin, macroscopic magnetism can emerge. In most materials, spins point randomly and cancel out. But in a magnet, vast numbers align, producing a field that reaches outward into space. A classic emergent leap. Countless invisible micro-decisions becoming a visible force. And then comes the truly unsettling part, superposition. In quantum theory, an electron is not always in one definite state before measurement. It can exist in a blend of possibilities, mathematically, up and down at once, until an interaction forces a single outcome. That transition is often described as collapse of the wave function, the narrowing of many possible realities into one observed fact. But if collapse is real, then the deepest question becomes unavoidable. Does a system collapse only when observed, or can it collapse on its own? Penrose rejected the idea that observation is the ultimate trigger. He proposed that nature contains a built-in objective mechanism that ends superposition, whether or not anyone is watching. His intuition was radical. Superposition is not just a property of particles. If matter is in superposition, then because matter shapes space-time, space-time itself must also be in superposition. Two different mass configurations would imply two slightly different geometries of space-time. And those competing geometries, he argued, create an instability. When the gravitational difference between the superposed alternatives becomes large enough, the system cannot hold the ambiguity anymore. It reduces, not because an eye looked, not because a mind noticed, but because reality itself insists on choosing. Penrose called this objective reduction, OR, not collapse caused by observation, but a self-terminating superposition caused by a physical threshold. And if these reductions are genuinely non-computable, truly unpredictable, then they represent something no classical algorithm can reproduce from first principles. Penrose wondered if consciousness might be built for precisely this kind of event. Tiny, irreducible selections of reality. But immediately, the brutal objection arrives. Quantum states are fragile. They require isolation, cleanliness, stillness, often extreme cold. The brain is the opposite. Warm, wet, electrically noisy, chemically turbulent. Under standard assumptions, quantum coherence should decohere almost instantly. For years, many critics argued that whatever consciousness is, it cannot depend on delicate quantum effects inside neural tissue. Penrose acknowledged the problem. In The Emperor's New Mind, 1989, he suggested that if quantum processes matter for mind, then there must be some special biological structure capable of protecting them, something he had not yet identified. Then, Stuart Hameroff entered the story. Hameroff, an anesthesiologist and neuroscientist, proposed a candidate: microtubules, tiny cylindrical protein scaffolds inside neurons, about 24 nanometers in diameter, built from repeating units called tubulin. Within tubulin, Hameroff argued, are hydrophobic pockets and aromatic structures rich in pi electrons. Electrons capable, at least in principle, of participating in quantum-like interactions. Under the right conditions, he suggested, these electrons might sustain coherent oscillations. Pairs of them could behave like informational units analogous to qubits. Microtubules, and arranged in complex geometries, could support resonant patterns and possibly even entanglement within and across neurons. This became the foundation of OR, orchestrated objective reduction. The idea is breathtaking in ambition. Microtubules orchestrate coherent quantum states. Penrose's OR provides a built-in, observer-free mechanism of reduction. Each reduction is a discrete moment of experience. A coordinated chain of such moments becomes what we call a continuous stream of consciousness. In some versions of the proposal, the timing of these events is linked to gamma activity in the brain, around 40 hertz, suggesting that what feels like a smooth inner flow might actually be composed of rapid, discrete frames, micro-instants of awareness stitched together so seamlessly that you experience them as one unbroken river. Like cinema, separate frames, one illusion of continuity. It's a seductive picture. Consciousness rendered from quantum uncertainty the way a computer renders images from code. But it's important to keep one foot on solid ground. OR remains controversial. The key claims, long-lived coherence in warm brain tissue, large-scale entanglement, specific microtubule computations, are still debated, and many scientists remain unconvinced. And yet the theory persists for a reason. It tries to explain something stubborn that classical explanations often leave untouched, the felt character of experience. Even anesthesia becomes part of the argument. We can describe many anesthetics in terms of ion channels, synapses, and neural firing. But the off switch of consciousness is still, in some respects, a mystery that invites multiple explanations. Hameroff has suggested that anesthetics may disrupt whatever microorganization enables awareness, whether that organization is purely classical or something deeper. Even xenon, an inert gas with anesthetic effects, has been used in discussions around this hypothesis, precisely because it seems biologically quiet, yet neurologically powerful. Some researchers have explored whether subtle quantum scale interactions could play a role. Again, intriguing, not settled. And then, inevitably, the story circles back to something you experience every night: sleep. Consciousness can fade without an external observer doing anything. In dreams, awareness becomes distorted, rich, chaotic, unanchored. In deep sleep, the sense of self disappears so completely that time seems to vanish. One moment, it's night. The next, it's morning. No felt interval in between. If OR were true, one could poetically imagine sleep as a change in the brain's internal rendering rhythm. Coherence reduced, orchestration weakened, the stream of moments thinning until the screen goes dark. And that brings us to the question that waits at the edge of every philosophy and every religion. What happens when the screen goes dark for the last time? Some interpretations, scientific, spiritual, and speculative, suggest that information may not be so easily destroyed. Physics itself wrestles with how information behaves in extreme conditions. Philosophies like Buddhism speak of continuity without a permanent self, patterns persisting, causes unfolding. Taoism speaks of returning to the source, like a drop of water returning to the ocean. Christianity speaks of the soul enduring beyond the body. In a metaphorical synthesis, one might imagine God, not as a human-like mind with moods and plans, but as a foundational reality, a timeless ground of law and order like the Tao, like Dharma, like the deep structure of the universe, the constants, the symmetries, the fabric upon which emergence builds layer after layer. Does that ground have intention? Does it have personality? Or is it simply the ultimate condition that makes everything else possible? We don't know. But the longer you stare at emergence, from atoms to life, from life to mind, from mind to meaning, the harder it becomes to believe that reality is made only of parts. It feels instead like a universe that keeps doing the same impossible thing. Again and again, it becomes more than it was. If you're still awake, you can continue to the next chapter. Otherwise, I hope you sleep deeply and dream gently. Good night.